Hey everybody, welcome into lecture number 28 of the semester. This is the last lecture of the semester and it's on more on Turing machines. So we're still covering section 13.5 of Rosen's text. Let's get right into it. So basically in this lecture we're just going to tie up some loose ends and talk about some open problems in theoretical computer science and kind of the mathematical end of computer science. So first of all, in the last lecture, we defined Turing machines and we talked about some different properties that Turing machines have. But it turns out that in practice, there are many different modifications that can be made to Turing machines. So we'll call this little section here types of Turing machines. And I'm just going to list some of the different modifications that can be made. And we'll talk about them a little bit and then talk about a pretty interesting consequence here. So some modifications that are made in practice to our usual Turing machines are the following. Number one, we could allow this is kind of the simplest possible modification that you can make. We could allow our direction set to have a direction that says don't move, basically, a blank direction. So we can allow a set of directions that instead of being L and R, is L, R, and then blank, the blank symbol here, and that just means that either you move left, you move right, or blank just means don't move. So you could call this D for don't move or something like that. But there is one modification that can be made, and so then it changes the state, changes the input, or rewrites the term on the tape, the symbol on the tape, but then it doesn't move, and it just goes to the next state. So the control unit just goes to the next state. So that's one modification. Another modification is that you could allow the machine to simultaneously operate on multiple tapes. So you could allow multiple tapes. And so this would obviously, you'd have to modify the input to the Turing machine. So it would be more than just a state and a symbol. There would have to be, multiple states, multiple symbols for the different tapes being used, and you'd have to somehow organize which one's working on which tape, or you could just run the same operation on multiple tapes at the same time, the same set of instructions at the same time on different tapes all at once, something like that. So there's another modification. A third modification that we could do is we could allow for two-dimensional tapes. And so what does this mean? I mean, the tape is already two-dimensional, but so two-dimensional tapes. And what this really means then is that you could have, instead of the tapes just being horizontal with the cells next to each other, this is what we mean by one-dimensional. Even though it's a two-dimensional tape, what we mean is that the grid would be two-dimensional in this case. So you could have something like this, and say your control unit is at this state, or it could even be, infinite two-dimensional in both directions. So it could go this way and this way, but you could move then, north, east, so this is northeast, right, etc. And so you could have then 9 different motions in your direction set, and if you want to include the blank one, you could have, that would be 8, right? But then you could have a 9th direction of don't move, right? So you could have your 8 directions from your compass, and then your 9th don't move, and you could have a two-dimensional tape that kind of scans along like this. And again, an infinite tape in all directions just extends like a plane, as opposed to a strip. So there's another modification. Number 4, let's see what I've got here for number 4. The fourth modification is that you could allow for multiple control units, multiple heads, that all read, so they all would be reading different cells at the same time. So multiple tape heads that read different cells. And then obviously would have to move in kind of different directions, right? And you might even allow for them to multiple heads to read the same cell, and then they'd kind of be locked in sync, I guess, if they were doing that. Well, they could have different states in the control unit, right? So even then it could be different. All right, so number 5, the other option here, and this is one that we're going to talk about later a little bit. I mean, we won't talk about it too much. This lecture is kind of just an overview of stuff that can be done in the future with Turing machines, but you can allow for non-deterministic Turing machines. So non-deterministic machines. And remember what this means. So a deterministic machine says that for every input, state, and symbol, SX, you get back, one output set of instructions. So one new state, one new symbol, and one direction, right? But the non-deterministic machines say, okay, maybe you could have multiple. So you could have a set of multiple outputs, S1, X1, D1, S2, X2, D2, etc., maybe all the way down to Sn, Xn, Dn. So non-deterministic machines are basically the transition rules do not form a function, right? A single function. They would be like a function with multiple outputs, which of course we know is not a function, but this is a modification that actually is made in, well, all of these are made in practice, but this one's done frequently in practice for the non-deterministic machines. And like I said, we'll get back to that a little bit later, at least in theory. And then, so all of these, you could argue, all of these modifications that we've suggested so far, you could argue that those increase the complexity of the Turing machine. So you would kind of say that maybe you would guess then that it would increase the capabilities, and we'll come back to that idea in a minute. But you could, on the other hand, think of trying to reduce the capabilities by restricting, instead of allowing for stuff, you could restrict to a finite tape. So don't allow for the infinite tape, but allow only for a finite tape, and then you'd have to put in some rules about what happens. What do you do when you get to the end of the tape, right? Do you go around, or do you just halt, or what happens when you end up at one of the ends of the tape? And so you would have to work that out. So here is the deal, though. So no matter which of these modifications that you make to a Turing machine, it turns out that none of these changes increase or decrease the power of the machine. So therefore none of them change the power of the machine. So none of these modifications change at all the power of the machine, the computing power. What do they do then? Well, they might make it much easier to build a machine that does a task that you want to do, but it doesn't make solving a quote unsolvable problem solvable, right? So in my notes here, I've written that these variations may make solving a particular problem easier. So you could maybe make it easier to solve a particular problem by allowing for a non-deterministic machine, or maybe for allowing two-dimensional tapes or something, right? But they will not allow you to solve a problem that a basic Turing machine cannot solve. So you cannot solve any new problems by making these changes. So it turns out that Turing showed that it's possible to construct what's called a universal Turing machine. I'm sure he didn't call Turing machines. They were named after him, probably later, but he showed that it's possible to construct, and this goes back to exactly what we were talking about just a second ago, but he showed that it's possible to construct a universal Turing machine. This is how the universal machine works. It takes in an encoding and then the set of instructions. So basically this can simulate the computations of any other Turing machine. That's the idea here. That's why it's universal. So I'll write it this way: of every Turing machine given an encoding of the machine and its input. So you have to encode the Turing machine T. So let's name this one T. Given an encoding of T and the input that you want to compute. So, and its input, let's call it X. All right, but Turing himself showed that such a universal Turing machine does exist, or at least theoretically exists. A Turing machine that will compute all Turing machine, every Turing machine. So that's pretty interesting. All right, so now what we want to talk about, a little bit more is more on the idea of computability for the rest of this lecture and therefore the rest of this semester. So item 2 in our lecture today is called the Church-Turing thesis. And we've been through enough math courses at this point that we're used to the word theorem Probably haven't seen thesis in a while. So let me state the thesis, and then we'll talk about why it's a thesis and not a theorem, and then a couple of consequences of it. So given any problem that can be solved with an effective algorithm, so this is the given portion, given any problem that can be solved with an effective computational algorithm, there is a Turing machine that can solve this problem. So there exists a Turing machine that will solve this. So basically, any problem that can be solved effectively, and this is where the thesis comes in. So any problem that can be solved effectively, so with an effective algorithm, can be done by a Turing machine. You can build a Turing machine to solve that problem. Now, the problem arises in what the heck does effective algorithm mean, right? And this is an informal and imprecise idea, okay? So solvability by effective algorithm. Really, it's the effective algorithm part here that is not well defined. So solvability by an effective algorithm. So this is a informal and imprecise idea. So informal and imprecise. This means that you can't just write down a definition of what it means, a mathematical, rigorous definition of what it means to be an effective algorithm. And for that reason, this can't be called a theorem then, right? We can't prove this using mathematical rigor. It's not a theorem. It's a thesis then. It's a thesis, okay? But we have some basic ideas of what it should mean to be an effective algorithm. So first of all, any problem that we can tell a computer how to solve nowadays is definitely should be effective, right? So any problem that can be solved by a modern computer should certainly be effective. So we'll call it effectively solvable here. Again, because this is such imprecise language, you'll find this effective adjective or this effective adjective kind of applied to many different terms here. So it's effectively solvable, effectively computable, effective computations, effective algorithms, all these different things that are really all imprecise. Anything that's effective is imprecise. So yeah, anything that we can solve with a computer should be effective because it's done with a computer, right? But actually, this is still more restrictive than what we want, right, by this statement, because computers have finite memory. Any computer that we build has finite memory, but a Turing machine has unlimited memory. So actually the class is even bigger than these problems, right? The class of effectively solvable problems is bigger than the ones that we can solve with a computer, or at least a current modern computer. So Turing machines technically have unlimited memory. They can just keep on going, right? So they have unlimited memory. And so the class of effective problems is actually larger, right? Larger than the class of problems that we can solve with a computer. So over the years, many people have tried to encompass what it means, try to make a definition basically of what it means to be effectively computable. So there are many theories of effective computation, effective computability. These have arisen. And it starts with Turing, right? So Turing came up with the Turing machine idea, basic, basic, everything that we've been studying up to this point, right? So Turing's theory of Turing machines. After Turing came Church, and Church came up with something called a lambda calculus, which you may have studied in other courses. We're not going to study it in this course. And then some other names that we've seen this semester came up with their own theories. Kleene had a theory. and Post had a theory. And it turns out that despite the differences, these theories are, on their face, not necessarily all that similar to each other. But despite all the differences in these theories, it turns out that these all define the same set of functions. So they all define, all these theories, the same set of functions, and therefore they're equivalent. All right. It's just different ways of like looking in the box, for example. So different windows into the box of the set of functions that are used to build the Turing machines in one sense. But they are all equivalent then. And so one consequence of this is that over, the 100 years almost since Turing came up with these ideas, really we haven't learned anything new. And so Turing's theory of computability and computers, basically, the advent of computers, in his mind, this came before any kind of modern computing, and we haven't really done any better since then, right? So Turing's theory is still, the best in one sense, maybe not the best in another sense, but there hasn't been anything better, right? So we haven't come up with anything better since Turing. We have honed in and done a really good job of, taking full advantage of Turing's theory, but we haven't come up with anything better, though. Than Turing's original theory. And like I said, that doesn't mean that like Turing had it all figured out. He didn't. We've done a lot of work since then, but the basic underlying theory of computers hasn't changed. We've just done a much better job of taking advantage of all the theory, right? And so implementing the theory. Okay, so that's the Church-Turing thesis, just some background on that. The last thing that we want to talk about this semester is computability and complexity of algorithms. So we'll do this in 2 items. Let's start by talking a little bit about, we'll just give some definitions here mostly, and then a little bit of discussion. But computational complexity. So there are a couple different types of problems that you could try to solve. So I'm just going to start writing down some definitions and then we'll talk about these. So the first definition is the definition of what's called a decision problem. And so a decision problem, I'll write a formal definition and then we'll give another name for it. And I think you guys probably have studied these in like I said, in other classes. But a decision problem asks whether statements from a class of statements are true. So you start with a class of statements, you take a particular statement, and then you determine whether or not the particular statement is true or not. So decision problems ask whether a statement from a class, a large class of statements that can be built using rules or whatever, right? Whether or not this is true. All right, so basically this turns out you can reduce this down to just the answer is either true or false or yes or no. So decision problems are also known as yes or no problems in some areas. So yes or no problems. A very particular kind of yes or no problem is a problem that's called a halting problem. So a halting problem, and probably the word halt itself gives you an idea of what this is going to be. So how we're going to state this, right? But a halting problem is a decision problem, or the decision problem. All right, A. It's a type of decision problem that asks whether or not a Turing machine eventually halts when given a certain input string. So decision problem that asks whether a Turing machine T eventually halts when given a certain input string. So this is definitely a decision problem because the answer is either yes it halts or no it doesn't, right? So the input string we'll call X here. And here's a theorem that is maybe a little bit surprising. But the halting problem is the halting problem is an unsolvable decision problem. This is the theorem. So it's unsolvable. And there's some exercises in the text, some recommended exercises that go over this idea and kind of prove it. It's an unsolvable decision problem. They at least sketch the proof of it. So the idea here is then, so what does this mean? Let's unpack it, right? So there is therefore no Turing machine. So I'll write this out. So there is no Turing machine. This is what this means. That when given an encoding of t and its input string x, can determine whether or not t eventually halts. So this is an impossible problem, unsolvable. All right. So what do I mean by that? When it eventually halts, when it starts, right? When it starts with with x written on its tape. Okay, so that's pretty surprising, pretty interesting. Like I said, in the exercises in the text itself, there's a couple exercises that outline how exactly this is done. All right, so how exactly you prove this. All right, so the last item that we want to talk about this entire semester then is computability. And computability works as follows. So a function, so we'll start with definitions, but a function that can be computed by a Turing machine. And we talked about this in the last lecture, how to compute a function with a Turing machine. We did addition, some other things, right? So different kind of functions. But a function that can be computed by a Turing machine is obviously called computable. And one that is not is called not uncomputable, right? So a function that is not, this is called uncomputable. And it turns out that every decision problem, from back up here, right? Every decision problem can be reformulated, I should say, as a functional computability problem, because the function itself is either you input the decision, you input the statements, right? And the output is either yes or no. So as far as a Turing machine and a function goes, the domain is a set of all statements and the output is yes or no. So every decision problem actually can be reformulated as a computability problem. Okay, so this, by the way, is how the previous theorem is proved, by using functions, computability of functions, as opposed to basic decision problem theoretical stuff. So we show that you'll show that the halting problem is not computable, basically, right? So the function, it's not as a function written as a function, it's not a computable function. All right, well, there are a couple now classes of problems, computability problems, that you've probably heard about, but these classes are called P and NP. So the classes P and NP. So in my notes, I don't have this as a new item, but I think we should put this as a new item here. We'll call this item 5 then. The classes P and NP. So let's just define these and then tie up all of our loose ends basically with a couple of comments about the differences in P and NP and what researchers are working on, thinking about nowadays. So the class P, these are called the polynomial time problems, also known as the tractable problems. Polynomial time problems, or these are also called tractable. And so these are problems that can be solved by a deterministic Turing machine. So remember, deterministic Turing machine, deterministic means that the set of transition rules, right, basically acts as a function on the inputs, on the state, comma, symbol inputs. It's a function, at least a partial function, right? But these can be computed, so a Turing machine, they can be solved by a Turing machine, a deterministic Turing machine in polynomial time in the number of terms of its input. So I'll tell you a little bit more about what this means in a moment. But polynomial time in terms of its input. And so obviously this is only useful if we know what polynomial time means. So let's take a little moment here and talk about polynomial time. So polynomial time is the following. So this statement right here, that the Turing machine solves the problem in polynomial time in terms of its inputs. I'm going to unpack that here. This means that there exists a polynomial P, which we are only going to care about the domain of integers. Okay, so I'll write it as P of n, although this is really the output of the polynomial, right? So we'll call this P of n, though, just to emphasize that it's working on integers, such that for all integers, really we need all natural numbers here, but that's okay, but all integers n, the Turing machine T halts in a final state Yeah, this is bothering me. I don't like this. So it's a polynomial P, but halts in a final state after no more than P of n transitions. And so now this is why it was bothering me, right? P is the polynomial. P of n is the output when input n, right? P of n transitions when the input length, or the length of the input, is n. So you put in a string of symbols of length n, and the machine halts in a final state after P of n transitions. So, certain polynomials can grow very quickly, right? As long as it's a polynomial, though, that bounds it, then you say that your problem is solvable in polynomial time. Okay? What about the class NP then? So NP, if you just guessed, you might guess this meant like non-polynomial or something, but that's not what it means, actually. This is the class of non-deterministic polynomial time. So the N is for non-deterministic. And these are the non-deterministic polynomial time problems. And these ones, you can probably guess now, these can be solved by a non-deterministic Turing machine in polynomial time. So same deal, right? In polynomial time. In terms of its input again. Okay, so these are the classes then, P and NP. Polynomial time is just something that we need to define either of or both of these, really. And so in the text it says the following. I'll put this in quotes because these are the words of Rosen. One of the most perplexing open questions in theoretical computer science is the following. So the question is, does P equal NP? Or does NP equal P? So these are sets of problems, right? So is every non-deterministic polynomial time problem also solvable by a deterministic model in polynomial time? All right. So this is an outstanding question. We don't know the answer, so it's open. So open means there's no answer to this, right? There are, though, so many people, by the way, have tried to solve this problem. I believe this is one of the new millennial problems in mathematics. So if you do solve this problem, I believe there's $1 million prize. So if you can answer this, does NP equal P? You could win a lot of money and really a lot of fame and probably advanced computer science in the process, right? Which would be just an added benefit. But there has been a lot of progress made, and there have been certain problems found called NP complete. So the NP complete class of problems, this consists of all the problems for which, if they are NP problems, right? But if they're also P, then all NP problems are P. So this is the class of NP problems, non-deterministic polynomial time problems, for which, if they are found to be also be P, then all NP problems are also P. So there's obviously a lot of focus on those problems, but to this day, none of those have been shown to be P, right? They're kind of like the problems which are on the edge, maybe just on the verge, right? And if one of them is found to be P, then it turns out all NP problems are also P. And at that point, NP and P are the same set. You don't really need to differentiate between the two anymore. We have seen, if we go back, let me check this. I'm checking the text right now. The question of whether, so determining whether a simple graph has a Hamilton circuit. All right, determining whether the simple graph has a Hamilton circuit, that's an NP complete problem. And also determining whether a proposition in n variables is a tautology. So that's also an NP complete problem. So those are two problems that we've seen. So Hamilton circuit of a simple graph. So given a simple graph, does it have a Hamilton circuit? That is one NP complete problem. And another one, I won't write this one down, but it's very similar actually. A proposition in n variables, is it a tautology or not? That's NP complete. So those are shown, both those problems are shown to be solvable in polynomial time by a non-deterministic Turing machine. And the question is if you can also solve it in polynomial time with a deterministic Turing machine in polynomial time, right? So anyway, I'll stop blabbing here. This is the end of the semester. So this lecture just kind of closes off some main ideas that we've studied this semester. Maybe leave some open questions like, does P equal NP? A big open question. And some ideas about just how you're going to use the information from this class in your future studies. So I hope you guys enjoyed this course, and I'll talk to you later.